Hi everyone, I am Sam Galotra. I am a postdoctoral researcher at the University of Chicago, and I'm going to present techniques for generating contrastive and counterfactual explanations. Before I start, let's go over a brief outline of the different topics that I'll cover today. We'll start with a definition of counterfactual explanations and look at a categorization of these explanation techniques. After that, we'll go deeper into a misconception in the literature of counterfactual explanations, where contrastive explanations are commonly confused with the counterfactual ones. After understanding these differences, we will review the background on causal inference and see how these can be used to generate counterfactual explanations. We will then look at the recent techniques that use ideas from causal inference literature to generate counterfactual explanations. In the last part of this section, we'll look into recourse, which is designed to help individuals with negative outcome to identify ways to flip the outcome of the ML model in their favor. Now, let's look at an example to understand the philosophy of counterfactual explanations. Consider Rosa from the adult dataset. The ML model predicts that they earn less than 50K income. Now, Rosa is wondering what can they do to increase their income. Counterfactual explanations are designed to answer these types of questions, where they model a counterfactual scenario, ensuring that Rosa has a different output from the ML model. Specifically, a key ingredient that is used to generate these explanations is the estimation of features that should be changed to flip the model outcome. Let us look at it pictorially. Consider a Euclidean space where each individual is a point. Rosa is denoted by the red point here based on her attributes. Now we want to identify the closest blue point, which is on the other side of the decision boundary. The blue point shown by the arrow is the counterfactual Rosa in this case. There are many different techniques which aim to identify minimum change in input attributes such that the model outcome can be flipped. These techniques are generally of two different types. First, feature-based explanation methods generate a counterfactual explanation score for every feature. This score characterizes the likelihood that changing the feature would change the outcome. Second, instance-level techniques calculate a counterfactual scenario for the input individual to generate different explanations. Today, we'll look at 5 different techniques, 3 of which are causal and 2 of those are non-causal. Let us start with inverse classification, which is a non-causal technique from a 2018 paper by Logel and others. This approach considers the input instance and aims to generate a counterfactual instance with a different classifier outcome. For example, we show the counterfactual Rosa, who has higher number of working hours to have income more than 50K. To generate such counterfactual scenarios, this approach follows a growing sphere algorithm which operates in 2 phases. First, it generates a sphere with the input instance as its center. The radius of this sphere is grown until it hits a point that has the opposite outcome, which is the favorable outcome in this case. In this figure, the red point is Rosa, and the sphere is grown until we identify the black colored cross. After identifying this point, the algorithm performs feature selection on this instance to ensure sparsity of changes while ensuring that it achieves the flipped outcome. This approach is highly efficient in identifying a new scenario that flips the classifier outcome, but it misses a key aspect of the problem, which is the dependency between attributes. For example, changing age attribute may affect many other attributes like work experience, hours of work, and so on. Therefore, it is possible that the counterfactual scenario that this technique generates is not possible in the real world. Now, let us look at another non-causal technique, which is RESP. This technique was proposed by Bertossi and others in 2020. This approach generates a counterfactual score for every feature as the expected difference in classifier outcome on changing the feature value. This score characterizes the impact of changing feature value on the outcome of the classifier. Where higher the score, the higher is the impact of changing the feature value. For example, let us consider Rosa as the input instance again, and we want to calculate the counterfactual score for the feature hours of Rosa. This approach identifies other individuals that have the same value as that of Rosa for all attributes except hours. So here it identifies two individuals, Emma and Jill. Each of these individuals have different values of hours, but all other attributes are the same. And out of these two individuals, one of them received a favorable outcome and the other one did not. Therefore, the expected outcome for counterfactual scenario is half, and the score for hours for Rosa is minus 0.5. In this way, this approach calculates the counterfactual score for every feature in the input. This counterfactual score models change in a single feature value, and this may not capture all possible changes in the features of the input record. Therefore, this approach has an extension to consider a contingency set, which models a fixed change in a set of attributes. For example, if the contingency set says age equals 40, then we consider a modified version of Rosa who has age equals to 40, and then construct feature-based scores based on perturbing the values of different features. Now, an advantage of considering a contingency set is that it is general to calculate score for any contingency. So we can vary multiple attributes, and once we vary those attributes, we can calculate scores for all other features. However, the approach still modifies a single attribute at a time to calculate the scores. And it does not capture the behavior of the system when multiple attributes are modified at the same time. Until now, we have seen two different techniques to generate explanations. These techniques aim to modify attribute values to generate explanation score. All these approaches modify attributes assuming independence. In reality, this does not hold and can generate an instance which may not exist in practice. If this is the case, the question is, are these techniques really counterfactual? Let us look at an example to verify this. Consider a counterfactual Rosa who has age equals to 44 and number of working hours equals to 65. This instance is generated by the techniques that assume independence of attributes. Now suppose Rosa has a preference that she wants to get married when she turns 40 and does not want to work more than 50 hours. If this is the case, we can never have a counterfactual Rosa who has age equals to 44 and number of working hours equals to 65. This instance, which prior techniques call as counterfactual, is actually not counterfactual, but it's a contrastive instance because it shows a contrast between the input instance and the current instance, where most of the attribute values are similar, but some of the attributes are different. And this contrastive instance can never be generated from the input instance, which is that of Rosa. And this is the key distinction between contrastive and counterfactual instances. More formally, contrastive explanations consider independence of attributes to generate explanations. An example of a contrastive data point are lookalike twins. The twins are very similar in terms of most of the attributes, but they are not the same individual. They are different individuals which go through different sets of reality and may have different outcomes later in life. In contrast, a counterfactual scenario captures dependence between attributes and models a hypothetical scenario where a specific attribute value was different from the original value. An example of this is Marty from the movie Back to the Future, where he meets his dad before his birth, hoping to change the future. In this case, we have the same individual, and the outcome is still affected by all factors which were there in the original instance. Now that we understand the key requirements of a counterfactual explanation, let us look at causal inference as an important toolkit to model dependencies between attributes. Causal inference refers to the study of cause-effect relationship between different variables in an environment. It is widely used in many areas like economics, agriculture, sociology, and biology. One of the common ways to capture the dependencies between different attributes is through a causal graph. This graph consists of each attribute as a node, and there's an edge from attribute A to B if B is functionally dependent on A. For example, age impacts education, so there's an edge from age to education in the graph. The nodes, which are labeled as U, are the unobserved variables. All attributes which are denoted in a 3D box are observed attributes. The causal graph is also accompanied with a set of causal equations that capture the dependencies between attributes. For example, the third equation, which is that of education, shows that education is equal to 0.4 times age plus 0.8 times gender plus the unobserved value of the education attribute, which is U education. Now, given this causal graph, we model the notion of an intervention as the case where we want to forcefully change an attribute value to some specific value, and this change is allowed to impact other attributes in the graph. For example, consider a case where the hours is intervened to 65. In terms of the causal graph, this phenomena is equivalent to removing the dependency of hours on which it was originally dependent. That is, cutting all incoming edges of hours and then adding a constant value 65, which is the intervened value of that attribute, as the parent of that node. After performing this intervention, the after effects of the change propagate through the graph and impact its descendants, like income in this case. Some of the advantages of considering a causal graph-based techniques for generating explanations are that the interventions are translatable to real-world interventions. These are more relatable to individuals and are robust against spurious correlations in the dataset. However, these interventions are complex procedures which require sophisticated techniques to estimate effects of an intervention. Specifically, intervention effects cannot be estimated in the absence of domain. The example at the bottom shows a causally consistent counterfactual ROSA where increasing age changes marital status and ensures that the number of working hours is less than 50. Now, let's look at some of the causal explanation techniques in this part of the tutorial. We'll start with Causal Shapley as the first technique. The causal notion of Shapley value uses the same formulation as it was described by Aditya in the first part of the tutorial. I won't go into the details of the same calculation, and I'll just focus on the key difference, which is the value function in this formulation. The value function is causal, which is shown at the bottom of the slide. Value of a set S is defined as the expected outcome of the classifier when all attributes in the set S are intervened to XS. Let us look at this definition with an example. Consider the causal graph for the adult dataset. In this graph, suppose the set S contains gender and number of working hours, and XS is gender equals female and working hours equals to 40. The value function is calculated by intervening on these attributes, that is, removing their incoming edges and conditioning gender to female and number of working hours to 40. The effect of this intervention then propagates through the network and it affects the descendants of gender and hours, which in turn finally affect income. And this final outcome of income is used as the expected outcome of the classifier. This approach is good because the number of interventions it considers are causally consistent, but it has a number of challenges, like it's computationally expensive to consider these interventions and requires additional domain knowledge to model the causal graph. Now, let us look at the second technique, which is DICE, which aims to generate a diverse set of counterfactual explanations for an input instance. For example, the two different explanations for ROSA are that Either they should increase their number of working hours to more than 65, or they should change education to masters and increase work experience by at least 1 year. The main advantage of generating diverse explanations is that it helps the individual, which is Rosa in this case, to pick any of the generated explanations based on their needs and understanding. The DICE approach generates these explanations by formulating it as an optimization problem to generate counterfactual instances based on three different objective functions. The first component of the objective function ensures that the generated instance is close to the original input instance. The second component of the objective function ensures that the different explanations are diverse. That is, they focus on different features or different modifications of different features. The third objective ensures that the changes required to generate counterfactual instances are sparse. That is, we want to make fewer number of changes to the attributes. These three different objectives are merged as a linear combination to write the optimization. This optimization problem is good enough to generate diverse explanations, but until now, we have not captured causal dependencies anywhere. Let us see how we can capture those. This approach captures causal constraints as additional constraints in the optimization problem and post-processes the output to ensure that it satisfies the causal dependency. For example, in case of Rosa, if increasing age, if the output explanation says that we should increase age and increase number of working hours to more than 65, it's not realistic because it's not causally consistent. So this would remove that as a post-processing. And then add this as a new constraint to the optimization problem and resolve the optimization problem. So in this way, this technique is able to capture causal constraints, but it does not capture any general dependencies between attributes. Additionally, this approach is highly inefficient as it may have to run the optimization problem multiple times to ensure that the generated outcome is causally consistent. Now, moving on, we present Lewis, which is a causal technique to generate counterfactual explanations, and this technique was published in SIGMOD last year. At a high level, Lewis generates explanations that are causal and contrastive in nature. These explanations model the counterfactual scenario by following the template of contrastive counterfactuals as shown here. Given an individual or a set of individuals with some specific attribute value who received a specific outcome, the outcome would be different with certain probability if the attribute value was the counterfactual value of that attribute. Let us look at an example to understand this approach better. Consider Rosa, who received a negative outcome from the ML model again. Now, Lewis generates the sufficiency score of an attribute, say hours in this case, as the probability that the outcome of the ML model would be in favor of Rosa if they worked 65 hours instead of 40. So when we change the attribute value of hours from 40 to 65, what is the probability that the outcome would flip for Rosa? Now, let us define the score generated by Lewis more formally. Forget the K in the notation for a moment. The sufficiency score of an attribute X on changing its value from X prime to small x is defined as the probability of receiving a favorable outcome O whenever X is intervened as small x for all individuals that receive the unfavorable outcome O prime and have the attribute value X prime. So for example, in the previous case, we saw that we considered Rosa, who received unfavorable outcome O prime and had hours equals to 40. We wanted to calculate the sufficiency score when we change hours to 65. Notice that the condition attributes characterize the subpopulation for which we want to estimate the score. Now, adding K to this definition, K refers to the context in which we want to calculate the score. More formally, it denotes a parameter to calculate score for any subpopulation. If K fixes all attribute values, then the score corresponds to that of an individual, which has that attributes. For example, in case of Rosa, we need to choose k equals to all the attributes she has. And choosing k as an empty set means a global score for all individuals in the dataset. As an example, intuitive meaning of calculating sufficiency score for changing hours from 40 to 65 for age equals to young evaluates the probability that younger individuals who received lower income when they had number of working hours equals to 40 will have higher income if they work for more than 65 hours. Following this notation, Lewis defines three different types of scores. First is the sufficiency score, which we already saw previously, which calculates the probability that improving an attribute value for all individuals that received a lower income would improve their income. Secondly, the necessity score considers the flip side, which calculates the probability that reducing an attribute value for all individuals that received high income would lead to a lower income. Third, necessity and sufficiency score calculates the probability that improving the attribute value leads to a favorable outcome and reducing it leads to an unfavorable outcome. These scores are calculated for varying context values, which is denoted by K, to generate explanations at global levels, which is the whole data set or the whole population level, or local levels, which is like the individual level or subpopulation level, which is like younger individuals, specific subcommunities like calculated by gender, race, or so on. In summary, we looked at 5 different techniques that aim to generate contrastive explanations. 3 of these techniques are causal, and 2 of them are non-causal. We saw that non-causal techniques are primarily contrastive and not counterfactual. In contrast, causal techniques capture dependencies between attributes, and counterfactual instances generated by them are translatable to real-world interventions. However, causal techniques generally require additional domain knowledge for estimation. Now, let's get to the last part of this section, where we look into recourse. Recourse aims to identify minimum cost interventions so that the outcome of the model gets flipped. Consider the same example of Rosa, who received a negative outcome, and now Rosa asks the question, what can I do to flip the outcome of the ML model? And let us look at 3 most popular techniques that study recourse and answer this question for Rosa. 2 of these techniques are causal, and 1 of them is non-causal. Let us start with the first technique by Uston and others, which is a non-causal technique. This approach models the problem as an optimization problem and writes a linear program to solve it. It considers the changes in feature values with parameters a1 to ak as shown here. And it writes the objective function of the linear program, which is to minimize the cost of changes, and writes the constraint that the classifier outcome for the input characterized by original input plus the change vector is favorable. The classifier function here is denoted by f. To solve this linear program, it assumes that the classifier function f is linear, and therefore it uses efficient LP solvers to generate a set of actions or the set of changes that flip the classifier outcome. As you may have guessed by now, this approach is non-causal and assumes that all attributes can be modified independently. Therefore, this approach can generate an outcome which may not be feasible in practice. Now, let us look at the first recourse technique, that is causal. This approach also formulates the problem as an optimization task where the goal is to minimize the cost of actions and a constraint is to flip the outcome of the classifier in the favor of the individual. These are the same as that of the prior work by Uston and others. But this approach has an additional constraint that the modified input is causally consistent. The advantage of this approach is that the additional constraint ensures that the output is truly counterfactual and is relatable to the individual. Now, let us look at a high-level overview of how it captures the constraint on causal consistency of the modified input. The approach assumes that we have access to the full causal model. That is, we have access to the causal graph over the attributes, and the dependency equations are also provided a priori. Under this assumption, it simulates an intervention and calculates the final outcome in terms of the input parameters. For example, consider a case where age and number of working hours can be intervened to solve the problem of recourse. Let the intervened value of age be small a and hours be small b, where both a and b are parameters. This approach intervenes the graph with these values and then propagates the effect in the causal graph to evaluate the final outcome, which is income in this case. In this example, the final value of outcome in terms of A and B is 20 times A plus 10 times B plus 30. Now, these causal dependencies are used as constraints in the optimization problem, and the output of this optimization is returned as the outcome for recourse. Now, this approach is highly effective because it captures the true causal dependencies and uses the causal equations to solve the problem. But the main limitation is its reliance on the dependency equations, which are generally not available in practice. We may still have access to the causal graph, but not the equation. Now, let us look at Lewis, which is the latest causal technique for recourse. This is a causal approach that also models recourse as an optimization problem, with a difference that it considers a constraint on the sufficiency of the changes in the original input, which captures the likelihood of flipping the outcome. Setting this threshold alpha to 1 means that the classifier outcome is guaranteed to flip, but choosing a smaller value of alpha means what is the probability that it denotes the probability that the outcome would flip for this individual. This formulation is also applicable at a subpopulation level, or because we consider the sufficiency score for, and it can be calculated for any context. It uses causal inference-based estimation methods to express the constraints and uses LP solvers to calculate the recourse. This approach does not require the causal equations, but it requires a causal graph for evaluating the sufficiency score. Until now, we looked at 3 different techniques for recourse, all of which formulate it as an optimization problem. One of the main challenges of these techniques is the reliance on domain knowledge to generate counterfactual instances. In addition to that, a critical need of these techniques that study recourse is their adaptability to evolving needs of the real world. And none of these techniques do that as of now. Consider an example where Rosa is recommended a recourse that age should be more than 40 and number of work hours should be more than 43. Now, currently Rosa is 34 years old and she waits for 10 years when she's 44 years old, and she comes back and observes that her income is still low. And the reason is, in these 10 years, the ML model has evolved, the dataset has evolved, the real world assumptions have evolved. And because of this evolution, the number of working hours required to have higher income is more than 50, and she has less than 50 working hours. Therefore, a key limitation of recourse is to remain consistent over time and space, because these are recommendations to the individual and which are made in the current date and time. But if these are the value of recourse do not hold in later in time when they come back, then it's not valuable to that individual. In summary, this part of the tutorial focused on contrastive and counterfactual explanations. We learned that counterfactual explanations capture causal dependencies between attributes, but contrastive explanations assume independence. We also saw that causal explanations are translatable to real-world interventions. The main limitation of causal techniques is their dependence on domain knowledge and their computational complexity. Lastly, we looked at the problem of recourse, where the goal is to identify minimum cost interventions to help individuals receive a favorable outcome. Most of the techniques in this space formulate it as an optimization problem, where the goal is to minimize the intervention cost and flip the outcome. Flipping of the outcome is used as a constraint. With that, I would like to pass the baton to Ramila, who would present data-based explanations and opportunities for research in our community. Thank you.